Okay, we're going to continue our theme of counting. This time we're going to be counting outcomes of actions that can get quite advanced. We'll be using this later for statistics and probability. Okay? And I'm going to show you quite a few little tricks to do some advanced counting today. Okay, let's try and see how many different outcomes can occur if something pretty simple happens. We flip a coin once, and then we roll a die. Okay, we flip a coin, then we roll a die. How many ways, or how many outcomes can occur? Well, let's see. We can have heads, then a 1, or heads, then a 2, or heads, then a 3, or heads, then a 4, or heads, then a 5, or heads, then a 6. That's if we have heads. What's the other possibility? That's 6 of them. We can have tails, then a 1, tails, then a 2, tails, then a 3, tails, then a 4, tails, then a 5, or tails, then a 6. So there's another 6 things, outcomes that can occur, isn't it? Well, that means 12 things can occur. Now that's a very simple couple of actions there. We want to come up with some shortcut. Now,
are you pondering what I'm pondering?
How many different flips can you get on the coin? 2. And how many different rolls on the dice? There is going to be a shortcut.
Excuse me?
Well, let's look at it again. What if we flip a coin a little more advanced? Flip a coin twice. How many outcomes can occur? Well, let's look at, so that you can see this clearly, we're going to use a tree diagram. Okay, and the first toss, only 2 things can occur. It's either going to be heads or tails. Okay, now, once we've decided that it's going to be, well, one of those 2, we'll flip it again. If it's heads, the first one's heads, then the second toss is either going to be heads or tails. And if the first one's tails, the second toss is either going to be heads or tails. Okay, this is kind of the idea of a tree diagram. If I put it upside down, it'll look like a tree. Now, how many possible outcomes can occur from beginning to end? Well, let's count the possible paths. We could have a heads, then a heads. We could have a heads, then a tails. We could have a tails, then a heads. Or we could have a tails, then a tail. So that looks like 4 possible outcomes. And we could come up with that shortcut again. 2 for the first action, and 2 possibilities for the second action. If we multiply that, I smell a shortcut. Now I want to make sure you see this pattern for these easier problems and how it's going to help you in the more difficult ones.
You'll come again.
For instance, what if we flip a coin 10 times? If I asked you to draw a tree diagram, I hope you appreciate that would be not very practical. It would take a long time. Okay, so we've got to come up with a shortcut, and I think you may already know it.
Here's someone who can help you.
We're going to use the multiplication principle. Okay, what is the multiplication principle? If an outcome, now that's the final outcome, consists of k successive selections, or a lot of little outcomes if you would, with n1 choices for the first selection, n2, that's the number of choices for the second selection. That's not n to the second or anything. The number of choices for the second selection, all the way up to the number for 3, the number for 4, the number for k choices for the kth selection. I don't know what k is going to be in each problem. Then the size of the big set A of possible distinct ordered outcomes, the number of outcomes for set A is going to be the number of outcomes for the first action times the number of outcomes for the second action times all the way up to the number of outcomes for the kth action.
Okay, so what I just heard, Blah, 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 blah.
Okay, let's actually do some examples. Hopefully you'll see what I mean. We're going to flip a coin,
Ooh, I'm dying!
like I said, 10 times.
This is a job for... You know who?
Let's use the multiplication principle. Okay, now we've got how many distinct actions here? 10. K is going to be 10. And each distinct action can have how many outcomes? 2. 2 times 2 times 2 times 2, etc. all the way out to 2 to the 10th power. So that the total number of outcomes here is kind of the product of all the small outcomes. And we get 2 to the 10th, or 1024. Much easier than a tree diagram.
I'm trying to think, but nothing happens.
For instance, how many possible phone numbers can there be in area code 301? How many possible? Holy mackerel. Okay, let's use the multiplication principle. Now consider, what is K going to be in this case? We've already decided the area code, so how many other numbers are there? 7 numbers. And each of those individual numbers that you dial, how many possible choices do you have? You have 10 for each of them. For the first one you dial, you could have 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9. 0 is a number now. For the second one you dial, could be 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9. Each of them, all the way out to the 7th number. So each of them is 10. So we end up with 10 to the 7th power, which is 10. You could have 10 million different phone numbers, and that's just in area code 301. See why you might want to count something like that.
Thank you, sir. May I have another?
Another thing you may want to count is license plates. How many spaces do we have to have on a license plate? Suppose we wanted to see how many possible license plates could be created where the first 2 characters were letters, and only letters, and they always ended with 3 digits. Okay, well, it's going to be a little bit different because the first 2 are going to be different than the last 3. The number of possibilities for the first character is one of the 26 letters, A through Z. Same thing with the second one. The first 2 we said in this problem are letters. Now it's going to end with 3 digits. Digits can be 0 through 9. Get the idea? And if you multiply all of those, you get 676,000 different license plates, and that's only with this distinction of 2 letters and 3 digits.
There's something I have to ask you.
Of course, it makes you think, oh, geez, I wonder how many Social Security numbers could be created.
Now I use my secret weapon.
I'm going to use the multiplication principle, okay? Now think about this. What is K going to be? How many digits are there in a Social Security number? There's 9 digits, okay? And each one of those digits can have how many possible outcomes? Well, 0 through 9. That's 10. Okay, 0 through 9. 0, and then 1, 2, 3, 4, 5, 6, 7, 8, 9. So actually, any digit has a choice of 10 different possibilities. So 10 to the 9th power, geez, how many different Social Securities can we have? One what? What is that? That's 1 billion, isn't it? 1 billion. Now we apparently, just the other day, passed in the population in the U.S.,
Does this answer your question?
past 30 million people. So we're good. We should be okay for Social Security numbers. But you know what? China would have more than that, wouldn't they? They would have to have 10 digits if they needed Social Security numbers. It's the kind of decisions you would have to make.
Hold on, little fires, dear.
Okay, now there's going to be some other tricks involved besides the multiplication principle. Okay? I wonder how many possible phone numbers contain at least 1 0. Okay, suppose your 0 button didn't work on your phone and you wanted to know if it was going to be okay. Okay, I wonder how many possible phone numbers could contain at least 1 0. Well, here's what we do. Find out how many total numbers there are. Okay, 7 digits. and 10 possibilities for each one. 10 times 10 times 10 all the way out to 10 to the 7th. That's the total. And we want to know how many have at least one zero. So let's subtract the numbers with no zeros. How many numbers have no zeros? Well, they have 7 digits, and if you don't include zeros, now it's not 10 to the 7th, but rather 9 to the 7th, because you're not allowing for the digit 0. It's only 1, 2, 3, 4, 5, 6, 7, 8, 9. So, if we take the total numbers and subtract the ones with no zeros, we'll have the ones that have zeros.
How do I do it?
And that's a trick that you should always consider. Okay, if maybe you can't find out count the number that you want, count the number you don't want and subtract it away. Okay? Let's do another one like that. Let's count the possible phone numbers that do not begin with 555. You know, remember those? That's the number they give you on the TV shows and on the movies. Okay, if they start with 555, it's a fake number, if you would. If a girl gives you number 555, she may not want to go out with you. Consider that. So let's find out the total number of phone numbers, which I guess would be 10 to the 7th, and subtract out the ones that do begin with 555. Well, how many are there that begin with 555? Well, the first 3 digits are set, 555. So that's the only thing that it's going to vary is the last 4 digits. And the last 4 digits we have no limitation, so it'll be 10 to the 4th power. The first 3 digits are set. So basically, it's going to be 10 to the 7th minus 10 to the 4th. I wonder how many numbers don't begin with 555. Oh, there's the answer. Okay, that's plenty.
Here's someone who can help you.
What about non-replacement tricks? A lot of times, what I mean by non-replacement is we're picking from a group and we're not putting it back. Show you what I mean. Always a problem at wedding receptions is seating people. I'll tell you a bigger problem is seating people that are in first grade, so they don't goof around. I wonder how many arrangements of seating 5 different boys and 3 different girls in 8 chairs. Well, let's see. We're still going to use the multiplication principle. The first chair has how many people you can seat in it? 8, the 5 and the 3. Okay, now, what I mean by non-replacement. The second chair, how many people can you put? You can't put that same person in the second chair. He's not replaced. So now you're down to 7. Okay, we're still using the multiplication principle. In the third chair, you're down to 6 and 5 and on so on down. And once you've used up 7 of the people, you only have 1 kid left. He only has 1 seat to sit in, so that's it. So the number of people is 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. That's kind of a tough thing to multiply, especially if you had way more than 8 people. So we have a special symbol for that. We call that 8 factorial. Now 8 factorial you can type in onto your calculator. What it means is it's the product of all the integers 1 through n. That's n factorial. All the integers 1 through 8 in this case. Okay, and by the way, just so things don't get messed up, 0 factorial will have to be 1. We'll talk about that later. Okay, and you can do this on your calculator. If you find the math key, and you'll have to hit the right arrow to move over to the probability area. Okay, you'll see it, and I'll show you it in just a second. And then it'll give you a different menu, and you'll have to go down, either down or hit 4, which is the factorial key. Okay, let me see. I should get 40,320 in this. Let me use my calculator to get 8 factorial. I'll show you what I mean. Okay, let me turn it on. And I need 8 factorial. So first I have to hit the 8. I want to get factorial, so I'm going to come on to math. And you see, math has various 4 different menus. So to move over to the probability menu, I'll use my cursor to the right. Actually, you have to do it 3 times to move on. And you see how it's changing as I move to the right. And the factorial is the 4th one down. Now I could cursor down, or I could just hit 4. Let me cursor down so you see what's happening. And I'll hit enter, and it puts in a factorial. So that's 8 factorial, and then I have to hit enter to have it actually execute. And son of a gun, I do get 40,320. Pretty cool, huh? Now there's other tricks that are going to be of use to us in addition to factorial. And one of them you've seen before.
I know, Professor X, that no other performer has ever dared to execute.
I think they have. I think you've seen Morgan's Law before. It was just called something else. Consider this. How many possible 3-letter passwords can we come up with, no repetition, so we're not going to put any back, chosen only from A, B, C, and D? Well, let's see. The first possibility, I have 4 possibilities. Okay, the second one, I have 3, and the third one, I have 2. So we get the idea. 4 times 3 times 2. I didn't need any help on that one. Let's do the same question though. Okay, but this time we're going to say the first letter must be C and the last letter must be D. Well, if the first letter must be C, we only have 1 possibility. Okay, and the last letter must be D. There's only 1 possibility. Now what's left? Just the 2 other letters. So there's really only 2 ways that could happen. It would be CBD and CAD. Okay, so that was easy. That didn't need any special help.
Very simple, sir.
Okay, ands are easy. It's the ors that are a problem. Let's do the same question, but the first letter must be a C or the last letter must be a D. How are we going to do this? Well, here's what Morgan's Law is. And I see if you haven't seen this before. The number of members in A union, remember union is OR, A union with B is the number of members in A plus the number of members in B minus the number of members in A intersection B.
I'm back, baby!
That's the inclusion-exclusion principle. Remember that from last class? Different name, but same thing. Okay?
Oh, yes.
I call it Morgan's Law when we're dealing with ands and ors. That's all. That's what a union is. Okay? A union B really equals the number in A plus the number in B. And you really counted the intersection twice. So we have to subtract the intersection. Remember? Because we counted it twice there.
Now then, boys, we'll see how much you learn.
Okay, let's see if we can do this. Once again, no repetition, chosen only from A, B, C, and D. We're going to create a 3-letter password, but the first letter must be C or the last letter must be D. Okay, well, the number of C unioned with D, which is C or D, is the number of outcomes of C plus the number of outcomes of D minus the number of outcomes of C intersected with D. Now let's think about this. The number of outcomes of the first letter being C. The first letter must be C. How many possible ways can that happen? Well, there's only 3 other letters, and then once I've chosen that one, 2 other letters. Okay, forget about any other situations. The first letter must be C. There's really going to be 6 ways, isn't there? Okay. Now, let's look at this. The other condition. The number of ways that the last letter could be D. Well, put the D in there. How many ways can the last letter be D? Well, the number of possible letters to choose from, once again, is the 3 left over, and once you've chosen one of those, there's only 2 left over. So the number of ways that you can do D as the last letter is 6. Well, how many ways, we had already figured out, can you have the intersection of these two things happening? In other words, C is the first letter and D is the last letter. Well, we had done that. There's really 2 ways, isn't there? So the number of ways that you can have C or D occurring there, or these 2 conditions, that C is the first letter or D is the last letter, is 6 plus 6 minus 2, or 10. You couldn't have done that without Morgan's law.
Chad, how do I do it?
Okay? When are you going to use Morgan's law? When you want to do an OR.
Thank you, sir. May I have another?
How many possible 3-letter passwords with no repetition can be chosen only from all the letters from A to Z? The numbers are higher here, but I really think that this isn't any more difficult. Let's see, we've got a 3-letter password. The first choice is 26 letters, 1 of 26. Now, you don't get any replacement here. You can't have any repetition. So once you've chosen one of them, you have to take that out of the list. And the second one only has 25, and the third one, consequently, you've taken 2 out, only has 24. So that's not too hard, is it? Whatever 26 times 25 times 24 is the answer to that. Now, once again, let me demo an AND. Let's do the same question. 3-letter passwords. We're going to take them from A to Z. The first letter must be X, and the last letter must be P. Well, the first letter must be X, so it's either X or X. The last letter must be P. Remember now, we're not allowing repetition. So the middle number, we have to take away the X and the P from the 26. So the only number of letters left is going to be 24. 26 minus 2. Okay? Gets you thinking, doesn't it? That was relatively simple, though, even so, with it, because it was an AND. Remember, it's the ORs that are the pain. Let's ask the same question, but we're going to let the first letter must be X, or another condition, the last letter must be P. Okay, one of those 2 things, either one or both. That's going to be a problem. That's when you're going to use Morgan's law. Okay, remember our first condition is that the first letter must be X, and our second condition is the last letter must be P. There's your Morgan. Okay, or the inclusion-exclusion principle. Remember that a union is an OR. Okay? Well, let's figure out first the number of ways that X can occur as the first letter in this 3-letter password. Well, that's not so bad. Separated, is it? Put X in there, and that leaves how many possibilities for the last 2? Well, we have to take X out of the list. So we have 25 possibilities. 26 minus 1. And then you've taken another one out, so the third one has 24 possibilities. Okay, so what is that? 600. Okay, that's the first condition, the number of ways that X can be the first letter. Shouldn't surprise you that it's going to be similar for the number of ways that P can be the last letter. Let's put it in there. It's P or P, right? And the other ones we have to pick from 25, because we took the P away, and from 24 because we took P and another letter away. So once again, that's going to be 600. Now we're going to subtract the intersection. What do you mean the intersection? The number of ways that X can be the first letter, and then at the same time P is the last letter. So it's going to look like this, isn't it? How many letters do I have to choose from if I've taken away X and P? Just 24. 26 minus 2, okay? So that intersection is just the number of ways that can occur is 24 ways. Okay? And if we add 600, 600, and subtract 24, we've used Morgan's Law to count this OR statement. Okay? I'm not going to live and die on this problem, but I do want you to remember that when we do an OR statement, we should be looking for Morgan's Law. Okay?
It is alive.
Very useful.
How about a little fire, Scarecrow?
Now there are other tricks. Okay? Addition tricks. Let's finish off today by using an addition trick of breaking a bigger problem into smaller, easier problems. Now this one is just the last one we'll do today, is only going to be broken into 2. Okay, but hopefully you'll get the idea. Consider I want to seat my 3 boys and 5 girls into 8 chairs that are in a row. Okay, and I want to see how many possible arrangements I can do that. One limitation here, the boys have to sit together and the girls have to sit together. Okay? Now, it's going to help us to draw a picture. But if you think about it, there's 2 ways to have the boys sit together and the girls sit together. Okay? Let's look at those 2 ways. And we'll look at them separately and then add the answers together. Okay? One way is if the boys sit on the left side. Okay? Now we have 3 boys and 5 girls. So, that would be one way, is to have all the boys on the left and all the girls on the right. So let's just deal with that. If we do that, how many people can we put in that first seat? 3. Okay, that's one of the 3 boys. Now once we've put one of them in there, how many do I have to choose from? 2, and then of course that whoever's stuck sitting next to the girl, that's the way it is. Now once I've done that, I have to start seating girls because I'm out of boys. How many girls do I have to start with here? It's going to be 5, and I'll work my way down. 4, 3, 2, and 1. Okay, and if you do all that multiplication, we'll get 720. Okay, now that's one way. The other way in this problem is, other than having the boys sit on the left, is to have the boys sit on the right. Okay, we're going to get a similar answer, but I just want to make sure that you see that that's different. Let's start with the first seat. How many girls do I have to choose from? 5. And then once I've picked one, 4, and on down to that one girl that has to sit next to the boy. Okay, now I'm going to start with the boys. How many boys in that first seat do I have to choose from? 3, and once again on down. Okay, and all that, I promise you, multiplies to 720. Now you've accounted for both ways. I hope you consider.
Are you pondering what I'm pondering?
We're going to add those, and that'll give us the total number of possible arrangements that you can put 3 boys and 5 girls into those 8 chairs, given that the boys have to sit together and the girls have to sit together. Okay, so those are some of the counting tricks that we'll be using in the future. I want you to practice them.
What's all this jabber-wopping when there's work to be done?
So let's get to it. Get to that homework. See you next time.